We're going to take a look at this last learning goal. It says, cite evidence used to develop and verify the scientific theory of the origin of the universe known as the Big Bang. We're actually going to start talking about what's known as cosmology, studying the universe. How did it start? What is it like? And these are some of the things that we are going to cover over the next, week or two. What does the darkness of the night sky tell us about the nature of the universe? As the universe expands, what, if anything, is it expanding into? Where did the Big Bang take place? How do we know that the Big Bang was hot? What was the universe like during its beginning years? What is dark energy? Or has the universe always expanded at the same rate? Finally, how reliable is our understanding of all of this stuff? A lot of what we're going to go over is in this book. It's called The First 3 Minutes. It was actually written back in the 70s and won the Pulitzer Prize. And it's not that long, but the stuff in it is very... You have to be focused while you're reading this. It's like a textbook on steroids. It basically goes over what happened at the beginning of the universe and how we know that. So the first 3 minutes of the universe, from the Big Bang to 3 minutes later. I recommend it if you're interested in this kind of stuff and you can sit still and focus while you read for more than about 5 minutes at a time. I want you to keep in your brain something that we learned last week. The universe is expanding. It's getting bigger. And every single second of every single day, distant galaxies are farther away from us than they were in the past, which means those galaxies are spreading apart. So just keep that in your brain as we go through today. All right, let's start. The edge center problem. What is that? I want you to imagine the edge of the universe. And it's not an edge of where all the stuff is. It's not like there's stars and galaxies here and then past that there's nothing. It's an edge to actual space. It's hard to put into words, but how can you make an edge to space? You couldn't reach past it. So if there is an edge of something that you can't reach past, because then it would be the edge of, you'd be past space, which just doesn't make sense. That idea, trying to visualize in your head reaching past the edge of space, just doesn't make sense. It doesn't make sense to us. So our brains assume that there is no edge to space. If there's no edge, if there's no edges, there's no center, which means there's no center of the universe. As much as you may want to think that it's you, common sense tells us that because there's no edge, there's no center to the universe. Another way to look at it is that no matter which galaxy you live in, you seem to be the center and everything else is rushing away from you. But if you go to a different galaxy, everything else is going to seem to be moving away from you. So there's no center, but everywhere is the center of the universe. But I want you to think for a minute. What if the universe was finite, which means it was not infinite, and it did have an edge? What if? What would that edge look like? Well, in that bread analogy that Brian Cox talked about a couple days ago, you could look at that loaf of bread as it expands and say, there is the edge. And the edge is expanding out into the air around it. You can't do that for our universe. If you blew up a balloon, we were supposed to do that lab where you drew galaxies on the surface of a balloon and then blew it up, the galaxies would move away. However, that is a 2D analogy of things moving away. There's no center of the outside of a balloon. So you can't say it's the center of the balloon because that's in a different dimension. The surface of the balloon, where would the center of that surface be? Or to make it a little bit more round, where would the center of the surface of a basketball be? You can't necessarily think of a center because any place could be considered the center. So thinking of the edge of the universe just doesn't make sense. There's no way to think of the universe having an edge. What about the beginning? How can we tell that the universe had a beginning? I want you to think about this. Do this thought experiment with me. Picture yourself looking out at the night sky, and what do you see? You see a couple stars, but for the most part, the night sky is dark. If you were up in space, you would see a couple stars and the night sky would be pitch black. It's very, very dark. But if the universe was infinite in size, and remember, you can't think of an edge, so some people want the universe to be infinite in size. If the universe was infinite in size, that means that no matter where you looked, if you go far enough, there would be a star there. If the universe was infinite in time, there would be enough time for that starlight to get to your eye. So no matter where you looked in the night sky, you would be looking directly at a star. No matter where you turned your head, your line of sight would end on the surface of a star. And the night sky would be very, very, very bright. But it isn't. And this is what's known as Olber's paradox. Heinrich Olber was an astronomer back in the 1800s, and he thought to himself, if the universe is infinite, no matter where I look, there should be a star at some distance. If the universe is infinite in age, then light will have had time to get to my eyes, and I should see light every single place that I look in the night sky. So we've just proved by contradiction that the universe is either not infinitely big, which means there are places that you can look in the night sky that don't end up on the surface of a star, or the universe is not infinitely old, which means maybe if it is infinitely big and everywhere it does end looking at a star, maybe light hasn't had time to get to us. Maybe you're looking everywhere and light is reaching your eyes, but it's redshifted out of the visible spectrum. Or maybe it's a combination of the three. The universe versus the observable universe. So the universe, that's easy. It's just everything. It could be infinite. It's every possible thing that exists. It's every single planet. It's every single alien. It's every single galaxy. It's every black hole. It's just every single thing. That was easy. The observable universe is everything that we can see. And that is definitely finite. The reason is that light has a finite speed. Light can't go faster than the speed of light. It doesn't travel at an infinite speed, which means that there is a distance away from us where light has not had enough time to travel. The universe is 13.7-ish billion years old. If you are 13.8 billion light years away, well, then light has not had enough time to travel through the universe and get to our eyes or our telescopes. That is what's known as the observable universe. Could there be things past that? Yeah, there almost definitely certainly is. We just can't see them because light has not had enough time to get to our eyes. So the observable universe is not an edge. It's not like you're in a room and you can't go past it. If you were there, you could fly a spaceship right past it. The observable universe is just an imaginary line. It's a place that's too far away for us to see. Light has not reached us from that area yet. In the future, it will, because more time will go by and light will have more time to travel. So if you come back in 1 billion years, then the observable universe will be 1 billion light years past what it is now. Alright, so the universe is expanding. We figured that out last week. We see the galaxies moving away, which means today galaxies are farther away than they were yesterday. So the universe was smaller yesterday, and last week the universe was even smaller. So just by running the clock backwards, the universe is going to shrink and shrink and shrink and shrink and shrink. And if you run it back fast enough or far enough, you're going to reach a beginning where all of the matter that's in our universe was closer in a single spot. And when everything gets to that single spot, whatever time that is what we refer to as the Big Bang. So we see everything expanding today, which means yesterday it was smaller. You just logically can run that backwards. Everything's going to get closer together, and when that happens, that was when the universe started. That was the Big Bang. So what is the Big Bang? It's a great TV show. If you haven't watched many episodes, I definitely recommend it. The Big Bang says that if there is no edge, there is an edge to the observable universe, but we don't know about the entire universe. There's no edge, then there's no center of the universe. Which means the Big Bang did not happen in some spot. The Big Bang happened everywhere. The Big Bang was when space came into existence. So if you are living in some part of the universe, The Big Bang is when that part came into existence. So the person sitting next to you is in a different spot in the universe. That spot came into existence. No matter where in the universe you are, that came into existence during the Big Bang. The Big Bang happened everywhere. So it's not like an explosion that happened in a location. It is the location. It is everywhere. And crazy enough, it's still happening. The universe is expanding. The universe itself is getting bigger. The Big Bang is still happening. The Big Bang is still going on. It started 13.7 billion years ago, but it is currently, the universe is getting bigger. The Big Bang is still going on. So if you run time backwards, and there's some point in the distant past where everything was in the same spot, that is what's known as the Hubble time. That is how far you have to go backwards in order to get to the Big Bang. If you remember, this graph here, this is the Hubble constant, the slope is the Hubble constant. This is the Hubble time. How long do you have to go back in time until the distance between everything is 0? In order to find that, you take the Hubble constant, which let's average it at 70. But if you take the current speed of how fast galaxies are moving away and say, at that speed, how long would it take for them to get back together? That's 14 billion years. That's why figuring out Hubble's constant, which is the slope of that line, how fast they're going, if we know that exactly, we can just say, at that speed going backwards, this is when they're all in the same spot, and that's when the universe started. The universe is roughly 14 billion years old, according to current observations of distant galaxies and their redshift. What's the farthest away thing that we can see? That's what's known as the Hubble distance. So the Hubble distance is how far can light travel during the Hubble time. So it's the speed of light times 14 billion years, also known as 14 billion light years, which means that we can see things that had their light leave 14 billion years ago. And if we're right here and we can see 14 billion years in that direction and 14 billion years in that direction, well, then the diameter of the universe should be 28 billion years, right? 14 billion light years this way, 14 billion this way, should be 28 billion light years. However, the universe is expanding. It's not just sitting here at 28 billion light years. Even if light has been traveling for 14 billion years, during that time, space has stretched and made space bigger. So that light, that photon might have been traveling from that star to our telescope for 14 billion years, but it traveled more than 14 billion light years because space has expanded over that time. So if the inflation of the universe, the speeding up of the expansion, is what we see it as today, then that object that was 14 billion light years away when the light was released is actually today 46 billion light years away. Let me repeat that because it's hard to wrap your brain around. The beginning of the universe, if something was 14 billion light years away, it would take light 14 billion years to get to us. Over that time, because the universe has gotten bigger, that object is now 46 billion light years away. And that object is 46 billion light years away, which means the diameter of the visible universe is about 92 billion light years. Even though the universe is only 14 billion years old, because the universe has gotten bigger, the diameter of the observable universe is 92 billion light years. Wrap your brains around that. And now that your brains are a little bit scrambled, here you go.
Let's talk about the whole universe. We can't see all of it. Some things are so far away that light from there hasn't reached us yet. So we're going to focus on the observable universe. That's the part that we, in principle, can see with light or gravitational waves. So how big is that? Well, it's a sphere with a radius of about 46 billion light years, or rounding down to keep it simple, about 90 billion light years end to end. Now that's crazy big, but it's even crazier that astronomers think they know that number. It's not like they measured the universe with a ruler, so how do they know? In a nutshell, you start with the age of the universe. The current estimate is about 13.8 billion years. That's the maximum amount of time light has had to travel to us. And then you work out how far away the emission point of that light is right now. And that's the radius of the observable universe. Remember, that distance is not 13.8 billion light years. It's much bigger. To understand why, it's critical to realize that space itself is expanding. A popular analogy that I wish I could take credit for is a loaf of raisin bread rising in the oven. Each raisin represents a cluster of galaxies in the dough space. Now, the raisins don't move through the dough, but as the bread bakes and rises, all the raisins get further apart from each other because the dough itself expands. Now, each raisin stays the same size. Galaxy clusters aren't expanding, and neither are individual galaxies or the Earth or people or trees. It's just the relatively empty space between those large clusters of galaxies. And not only does the dough expand, it can expand at different rates during different stages of the baking process. Maybe really fast for 1 billion years, then slower for the next 2 billion. These two facts, the expansion of space and the fact that it can expand at a variable rate, complicate how we measure the size of the observable universe. In fact, space itself can expand at any rate it wants to, even faster than the speed of light. So over the lifetime of the universe, the birthplace of a beam of light can be carried ridiculously far away by the expanding space dough. To know exactly how far, though, and calculate the size of the universe, you need to know how quickly space has been expanding at every moment in history, ever. So how can we possibly know the expansion history of the universe? Using something called cosmological redshift, which is like a fingerprint that the expansion of space leaves on beams of light. Let me take a moment to explain. Light has a color determined by its wavelength. Longer wavelength light is redder, shorter, bluer. If space were not expanding, then light from a distant galaxy would be the same color when it arrived on Earth as it was when it first set out. Blue on departure, blue on arrival. But because space is expanding, the wavelength of light gets stretched as it travels to us, making the blue light red, hence the term redshift. In more extreme cases, the wavelength can be stretched out of the visible spectrum altogether into microwaves or radio waves. Now, here comes another important point, so pay attention. The light from more distant galaxies is redshifted more than light from nearby ones. You see, the light from more distant places has further to go, so it spends more time in the expanding space, in the rising dough, and thus it has its wavelength stretched more. Makes sense, but how are redshift and distance related quantitatively? That is the million-dollar question. If we knew the answer in numerical detail, we could figure out the expansion history and in turn the size of the universe. So can you do this? Can you measure the distance-redshift relationship? No sweat. Just find a bunch of faraway galaxies, much further than Andromeda, measure their distances and their redshifts, then put those distances and redshifts on a graph and find the best fit curve. Voila, you now know the distance-redshift relationship, and from that, how fast the universe was expanding at every moment ever. Once you have the expansion history, how do you actually determine the size of the universe? Remember, as I said a long time ago, we first need to get the universe's age. So let's go back to the raisin bread. If we run the movie of the rising dough backwards, at the rate given to us by the expansion history, eventually nearby raisins will sit on top of each other. That is the Big Bang, and how long it takes to get back to this point is the current age of the universe. Our best current estimate, using that expansion history, is 13.8 billion years, give or take. Step 2 is, well, annoying math, but we can represent it visually as follows. Imagine that, seconds after the Big Bang happens, every raisin emits a beam of light that can then travel without hitting any obstacles. As we run the movie forward, at the rate given to us by the expansion history, those imaginary beams would travel through the expanding space and reach us at different times. One of those beams of raisin light would be just reaching us as the clock hits 13.8 billion years. We then see where that raisin is now. Answer, about 46 billion light years away. Boom. So that's how we know that the observable universe is about 90 billion light years in diameter. But what about the unobservable universe? Aren't there galaxies even further away whose light hasn't reached us yet? Well, yeah, there are, but I'm afraid that's a subject for another episode.
Another way to think about this. Galaxies are moving away from us faster and faster. If you are farther away from us, you are moving faster away. A galaxy that's farther is moving even faster. A galaxy that's farther is moving even faster. Which means there has to be a distance away from planet Earth where that galaxy is moving away from us at the speed of light. Doesn't mean that that galaxy is traveling at the speed of light, but it means that the distance between us and that galaxy is increasing at the speed of light. And now to break your brains just completely in half. Will light from those galaxies receding at us at the speed of light, will light from those galaxies ever reach us? Why or why not? Big Bang was the beginning of the universe. How big was it?
Just how big was the Big Bang? The idea that the universe is expanding as the result of a single explosion wasn't always universally popular. In fact, the term Big Bang was coined in 1949 by astronomer Fred Hoyle as a way of sarcastically dismissing it. But thanks to Edwin Hubble, we now know our observable universe is expanding. And extrapolating backwards, we can tell that 13.7 billion years ago, it was all compacted into one superdense ball. And this singularity expanded and cooled to become everything in the universe that we see around us. So though the Big Bang involved everything in existence, its beginnings were really quite small. And after measuring the background radiation in the universe, astronomers have worked out that the Big Bang was only around 120 decibels, about the volume of an average rock concert. So while the Big Bang still has a lot to teach us about the universe, we do know, at least to start with, it wasn't particularly big. And it wasn't much of a bang either.
How do we know that all of this happened? It's a good question. How do you know that scientists aren't just making it up? There's 3 big reasons that we know that it happened. I'm going to go over each one of these a little bit more in depth. The first is the abundance of light elements. So how much hydrogen and how much helium exist. What we see is exactly what math predicts, exactly what we expect to see based on how we understand nuclear physics. Number 2, galaxies seem to be moving away from us. Logic tells us that yesterday they were closer, last week they were closer, last year they were closer. You just go back far enough and you get everything at the same place. And number 3, if the universe used to be very small and dense, that means it also would be very hot, just like the core of a star, which means we should be able to find some of that leftover heat. Let's go over each one of these. Nucleosynthesis, the making of atomic nuclei. Nucleo means nuclei. Synthesis means to make something. Based on our current understandings of nuclear physics, we can determine how much deuterium there should be, which is hydrogen with an extra neutron, how much helium there should be, which is what happens when 2 hydrogens smash together, and the amount of each regular hydrogen, deuterium, and helium, the amount that we predict matches exactly what we see up in the sky. So at the beginning, the universe was very hot. It was very, very condensed, very, very hot, like 10 billion degrees. Neutrons, protons, electrons, neutrinos, positrons, all flying around. As the universe expanded, it cooled down a little bit, and neutrons either decayed into the proton and electron. Remember, if you take an electron and smush it into a proton, you get a neutron? Well, if you go the other way, you can get a proton and electron out of that neutron. So neutrons either decayed apart into a proton and an electron, that's a hydrogen atom, or they smashed into a proton and made deuterium. That deuterium sometimes came together to make helium. So we know that there should be some regular, just protons floating around, hydrogen atoms. There should be some deuterium, and there should be some helium. And what we calculate is exactly what we find. About 25% of the elements that we find should be deuterium, about 25% should be helium, and a very tiny amount should be lithium. We find exactly that. So our mathematical models of how nuclear physics works matches what would happen if the Big Bang happened. So we weren't there, but our math tells us that that happened. 2, the universe is expanding. So we run the clock backwards, and the universe gets smaller, 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 smaller. So eventually you get to everything in the universe is in the same spot. I'm not going to go over that a whole lot, because that one just kind of makes the most sense. Finally, the CMBR. I want you guys to do another little thought experiment with me. Imagine the entire universe, not just our galaxy, but the entire universe is filled with firecrackers. And somebody sets them all off at once, instantaneously. What would you hear? Would you hear one giant bang? Or would you hear a continuous roar? You would actually hear a roar because the fireworks closest to you, the sound would get to you first. The fireworks that are a little bit farther away, then the sound would get to you. The fireworks that are farther than that, then the sound would get to you. So because sound has a finite speed, there would always be some sound from more and more distant firecrackers reaching your ears. Light does the same thing. This is a picture of light that is constantly reaching us from farther and farther and farther away. This is what's known as the cosmic microwave background radiation, the CMBR, one of the most important discoveries in science. This is that leftover heat from the Big Bang. Let's figure out how we found it. All right, so in 1948, we realized that the universe was expanding, which means if you run the clock backwards, it should get smaller, denser, and hotter. And George Gamow, who I believe won the Pulitzer Prize, kind of thought to himself, if it was small and dense and should radiate like a black body, it should be giving off light. If the universe was super hot, it should give off light, and we should be able to detect that. Two other physicists figured out that if the universe was giving off light 14 billion years ago, they figured out how hot it would be, what wavelength of light that would be, and how the expansion of the universe would redshift that from above gamma rays down through X-rays, visible light, infrared, microwaves, and now it should be somewhere between the microwave and radio wave wavelength. We're going to skip ahead a decade. Penzias and Wilson are using a radio telescope to study different things up in the sky. And as they're doing that, they keep hearing this weird, peculiar noise. And they think something is wrong with their telescope. So they go out and realize that a bunch of pigeons had been nesting in their telescope. You can see that there's like a giant opening. So a bunch of pigeons got in here and basically pooped everywhere. There's a bunch of bird poop all over the inside of their telescope. They're like, well, that's not good. That's probably what's causing this weird noise. So they literally, two like PhD physicists are out in their telescope scooping bird poop. They go back after they clean their telescope and the noise is still there. Now what? All right, what could it possibly be? The noise did not go away. Over at Princeton, a physicist named Robert Dicke realized that with our current technology back in the 60s, we should just about be able to detect that redshifted energy, that redshifted light, that redshifted radiation. Penzias and Wilson heard about this idea that we should be able to detect that redshifted radiation, and then they thought to themselves, wait a minute, if we should be able to detect this radiation and we're detecting some weird radiation, some weird static, maybe we are detecting this hypothesized afterglow of the Big Bang. They didn't want to just jump to conclusions, so they pointed their telescope in every direction. They called other astronomers, and they also were starting to pick up this random radiation from every single direction that they could point their telescopes. Turns out they had found the cosmic microwave background radiation. They had found leftover heat from the Big Bang. Because this is leftover heat from the formation of the universe, every part of the universe, every single square inch of the universe should have some of this radiation in it. The temperature of that radiation should be roughly 3 degrees above absolute zero. It's like negative 450 degrees Fahrenheit. Very cold, but not zero. So there should be some temperature up in space that all of space is that temperature. And in 1992, the COBE satellite measured the temperature of space to be 2.75. That black body radiation that was coming from everywhere has a temperature of 2.75 degrees. Pretty darn close to what the mathematicians came up with. The history of the cosmic microwave background radiation. This is what Penzias and Wilson saw, this little fuzzy line right here. Where is this coming from? A couple decades later, COBE went up and measured the temperature of space, and that was the map that they got. A decade after that, WMAP went up and measured much more precisely. And a decade after that, we finally have the Planck satellite. And to date, I believe this is the most detailed map of the cosmic microwave background radiation. What you are looking at in this photograph tells us a couple things. The red and blue are temperature fluctuations that are like that big, like very small temperature fluctuations. But when the universe was little, it only had to be that big. As the universe expanded, each little fluctuation got a whole lot bigger. And these little fluctuations ended up causing there to be galaxies or not galaxies. So we are looking at a couple things. We're looking at the temperature of the universe, right when it was a baby. We are looking at the light that was given off because of that temperature, right when it was a baby. So we can see this light, and that light is in the microwave part of the spectrum, and that tells us the temperature using blackbody radiation of the little tiny baby universe.
If you look up at the night sky in any direction, past all the stars and more stars and galaxies and superclusters of galaxies, you will see light that has been traveling for 13.7 billion years to reach Earth. It's the oldest and most primeval light in the universe, a picture of our cosmos in its hot younger years, and it's called the cosmic background radiation. Of course, you can't really see this light with your naked eyes because it's in the microwave band of the electromagnetic spectrum. But it is visible to radios and radio telescopes, and even makes up a small portion of the salt and pepper on an analog TV. Where does this luminescent background come from? Well, just after the Big Bang, the entire universe was still so small it would have been very dense, scorchingly hot, and because it hadn't yet had time to get rough and uneven, it would also have been scrumptiously smooth. For a while, things would have been so sweltering that electrons didn't settle down as parts of atoms or molecules, but instead roamed freely in a kind of red-hot cosmic soup. That soup would have had lots of light bouncing around it too, scattering off of electrons and protons like a hall of mirrors. However, as the universe expanded, there was less and less energy to be had in any one place. And when things had cooled to just below the temperature of the sun, pairs of electrons and protons no longer had the energy to resist each other, and they fell into the electromagnetic embrace we call the hydrogen atom. These electrons were so enamored by their new proton love interests that they effectively began to ignore all the light bouncing around them. So with fewer free electrons for light to interact with, the universe suddenly became transparent, and all the pent-up light was sent forth in whatever direction it had been headed after its last scattering, doomed to travel alone and unnoticed through the cosmos. That is, until it bumps into something solid. When we finally see it here on Earth, this light has been stretched so much by the 13 billion year expansion of space that, like a record slowing down, its frequency and color have shifted from the original sunlight white all the way to cool microwaves. Thus, it's often called the cosmic microwave background radiation, or CMB. And just as we can tell the temperature of a red or white-hot iron from its glow, this light tells us the temperature of empty space, currently around 2.725 Kelvin, or minus 270 degrees Celsius. However, the universe isn't exactly 2.725 Kelvin in every direction. If we look closely, there are small and seemingly random but noticeable bumps all over the place, kind of like milk that's starting to curdle. Our best understanding is that these cosmic curds formed as quantum fluctuations in the otherwise creamy infant universe, and then began to coagulate as the universe cooled and expanded. It's hard to overstate just how small or unbumpy these fluctuations of temperature and density were to begin with. The hot or cold spots were only hotter or colder than their surroundings by a factor of about 1 in 100,000. That's like noticing that a bacteria makes a beach ball bigger. But while this clumping of the universe initially resulted in small variations like the ones we see in the CMB, later on the chunky curds of primordial soup attracted each other gravitationally, and they ultimately coagulated and coalesced to form all of the massive structures in the universe that we see today, like planets, stars, galaxies, and superclusters of galaxies. So when we look up at the night sky past those galaxies and see the ancient light of the cosmic microwave background radiation, we're literally seeing the starting point, the proverbial cream, if you will, from which the starry curds of the universe congealed. Or quite simply, proof that the moon really is made of cheese.
There are more pieces of evidence other than these, but these are the big three. A lot of people want to say the Big Bang is just a theory, but if you remember, a theory in science has the most data to back it up, which means the Big Bang has more data. More data, more evidence, more observations than any other hypothesis or idea of the nature of our universe. The Big Bang, according to science, is what happened. The Big Bang happened. I appreciate you calling. Thank you so much.
No problem. If I have any other questions, I'll reach out.
Perfect. All right, bye. Roar.